Hello, so today's lesson is on acceleration. So just going to get you to watch a little bit of a video. This is the rocket car at Santa Pod Raceway. Just want you to think about what this might feel like. How would you describe the feeling of acceleration? So I'll play you the video. I've got to fast forward it a bit because it's a lot of just revving the engine. So if you can see on that racetrack, Santa Pod racetrack, is 1/4 of a mile long. And that rocket car, did it in 5 seconds. Okay, some cars can't even get from 0 to 60 in 5 seconds. In fact, most cars can't. And it did 1/4 of a mile. It went 298 miles per hour. What must that have felt like to the person inside? Incredible. So we're looking at velocity and acceleration today. For bronze, we need to know the difference between speed and velocity. For silver, be able to describe the difference between acceleration and deceleration, and for gold, be able to calculate acceleration and deceleration. So I'm going to talk to you about velocity and speed in a minute. So I want you to watch the snail at the top. Now the snail at the top is going to do a 20-meter run, okay, in 5 seconds. There it goes, in a nice straight line. Now if I wanted to calculate the speed of that, we know from previous work at Key Stage 3 that speed is distance divided by time. So the snail travelled 20 metres, okay, and the time, and I know the time because I set up the animation, was 5 seconds. So I know that 20 divided by 5 gives me 4. So that snail would have to be travelling at 4 metres per second. Quite a speedy snail. So speed is just a number, okay, 4 metres per second. Velocity is similar to speed in many ways. So instead of distance, we have displacement. Now, displacement is the distance between where you started and where you ended. Okay, and in this case, the distance from where we started to ended is in a straight line. So it's still 20 meters. And we did it in 5 seconds. So we get the same speed. Okay, 4 meters per second. But velocity is speed in a direction. So we have to say what direction it's going in. Okay, and in this case, we can just say the snail was travelling to the right. So that turns our speed from 4 meters per second into velocity by saying to the right. You could say forwards, backwards, up, down. Okay, but in this case, the snail was going to the right. But the speed we get, the number we get, or that we call that the magnitude, is the same in both these cases. In this case, we're going to make the snail go round a circular track, and it's 20 meters again, but in a circle. So if we look at the speed, okay, the distance travelled by the snail divided by the time. Now I kept the same time, okay, even though it's going in a circle, the distance was the same, 20 divided by 5, 4 meters per second. So if I said to you, right, the snail's moving 4 meters per second, you wouldn't know if it was moving in a straight line or in a circle, or any way. My velocity would tell me that though, and in fact this velocity is displacement divided by time. Interestingly, when you travel in a circle, you start at the same point that you end up at, and so the displacement of the snail is actually 0. It started at the start and it's ended up at the start. So the velocity would be 0 divided by 5, which gives us 0. And here we get a different number here. Really interesting. Now, most of the time you won't need to worry about that. It's just an interesting point. Most of the time you just need to remember velocity would be 4 meters per second to the right. This sort of leads on to A level, okay? But I just thought it was interesting to put in, and you could see the difference there with the snail. So speed is how fast an object is travelling, distance divided by time. Velocity is how fast an object is moving in a direction, displacement divided by time, and the directions you could put would be left, right, up, down, north, south, etc. And remember, displacement is the direct distance from the start point to the end point. And if you move around in a complete circle, the displacement is 0. Okay, so this gives an example of that. If this was a path you walked, here's the distance you walked, but the displacement would just be from the start to the end and is often shorter. You might want to pause the video here and take some notes. Just wanted to show you a couple of videos demonstrating the difference between acceleration and deceleration. So here's a car accelerating. And then here's a car, two cars decelerating actually. This video is in French, but it's trying to show you the difference between how quickly a Formula 1 car can stop compared to a normal car.
Et voici à présent un test hors du commun. Un test de freinage comparatif entre une Formule 1 et une voiture de série. Derrière le volant, rien moins que Ralf Schumacher et Juan Pablo Montoya, les pilotes libres des Bundesliga. Une Formule 1 freine comme aucune autre voiture. Quelques secondes suffisent pour passer de 200 à 0 km/h.
So they're going to decelerate now. So decelerate, slow down.
Les deux voitures freinent exactement.
You can see what a difference there is made by the Formula 1 car compared to the normal car.
S'arrête 32 mètres plus loin. Voici le test vu sous un autre angle.
Okay. Right, next we're going to move on to the silver task. We're going to start looking at velocity time graphs. So here is some times, okay, so 10 seconds, 20 seconds, 30 seconds, 50 seconds. Here's some velocities, okay. And what I want you to do is draw this graph in your book, okay, and then I want you to add these points. So plot 0, 0, okay, 10, 10, 20 in 10 seconds, so it's going to be 20 to here, 30 at 40 seconds, and then 50. In fact, I've made a mistake there. I need this to be 20, not 10. Sorry. Okay, so I want you to plot that, and then I want you to draw the lines. So it will look something like this, okay? So plot it yourself, and then you can check it on the next one. So we looked at distance time graphs last time. With velocity time, it's telling you about the speed. So a flat line does not mean it's stopped. It means something different. So on a velocity time graph, you need to look really carefully at the question. Is it asking about distance time or velocity time? It is telling you the speed. So if we look here, a diagonal line upwards means that the speed is increasing. So you're getting faster. That is called acceleration. And if the line is straight, it's constant acceleration. When the line flattens off, it doesn't mean you've stopped. It just means your speed or your velocity is constant. So you're just staying at a constant speed, okay? Constant speed. This line is steeper, but it's increasing. So we are accelerating, but at a greater rate than this one. So this one is a greater acceleration, like putting your foot down more in a car. And then a diagonal line downwards would mean decelerating. And you can see we've gone from a high speed to no speed. So we've stopped here. You might want to pause the video there and take some notes. Gold task is looking at acceleration, although it's fairly simple to calculate. Acceleration would be the change in speed velocity divided by the time taken. Now the symbols we use for this equation is A equals V minus U over T. So A is acceleration, and it's measured in meters per second squared. That stands for meters per second per second. So it's how quickly you increase your speed in a second. V is the final velocity, so what you end up at. And U is the symbol for the initial velocity, what you start at. And T is the time taken. So we're going to look at a person is driving in a car at 13.4 meters per second. They see a traffic light turning red and they come to a stop. So this is really important. It means that the final velocity is 0. And the time it takes is 1.43 seconds. What is their acceleration? Give your answer to the appropriate number of significant figures. First thing to do, write down what you know. So we know u, which is what we started at, 13.4. We know v is 0 because it stops, and we know t is 1.43. So if we do the calculation, a is v minus u over t, we're going to do 0 minus 13.4 over 1.43. And that gives us a minus 9.4 meters per second squared. And the minus usually stands for deceleration. You can press pause here and take some notes. Just going back to our graph then that you've drawn, we can calculate the acceleration from this graph by using the gradient similar to a distance time graph. So we do the change in velocity divided by time. So if we look at section O to A, which is this first line here, the first line, the change in velocity is from 0 to 10, so that's 10. And the time taken is 10 seconds. So 0 to 10, change in velocity, 10 divided by time taken is 10, which equals 1. If we look in the next section, A to B, the line is flat, so the change in speed is 0. It stays at 10 meters per second. And the time that takes is 10 seconds. So we get 0 divided by 10, which is 0, which means we're moving at a constant speed. There is no acceleration. This line is steeper, so the change in velocity will go from 10 to 40. Okay, so the difference is 40 minus 10, which gives me 30. And the time that took is 10 seconds. So 30 divided by 10 is 3. Okay, and we can see that number is higher than this number, which means it's a greater acceleration. And then the last one, okay, we've got a deceleration here, we know because the line is going down. So we end up at 0, so the change in velocity is going to be 0 minus 40, because that's what we started at. And the time that takes a bit longer this time, 20 seconds. So we're going to do minus 40 divided by 20, which gives us minus 2. And the minus just means that we've slowed down. Okay, that ends the slideshow there. There's various tasks for you to do. You only have to do one task. Wish you the best of luck. And again, remember, physics is difficult. If you need a hand, contact us. We're here to help you. Thank you.